We can use fermentation. We can take foods that are going out, so spoiled or a little bit defective, and upcycle them through fermentation. We can take those lactic acid bacteria and ask them to ferment imperfect fruits and vegetables and make them into a new product or desirable again. When we ferment, we're preserving food. What's pretty fascinating is that, if we have cabbage or we have a cucumber, we know generally that's healthy. And what happens when we add a little salt and let those microbes grow? They're digesting the food for us, so they're making it more easily digested by us. But those microbes are also giving new bioactive compounds to these foods. So I really think what we're seeing is that, these microbes are changing milk, berries, cabbage, etc., into something that is more nutritious than what we started with. So fermented foods are living foods, and anything that's alive is kind of unpredictable. I think that's why through most of the industrialization of our food supply, chemistry was the answer, adding compounds. Maybe the past 10 years we've turned a page to go back to say, what is the biology of the foods we eat? So with that comes a lot of opportunity, but also the issue that microbes' life can be unpredictable. So just as we need microbes to make fermented foods, some of those same microbes, or sometimes unwanted contaminants, contributors, make the foods spoil or have quality defects in how they look or how they taste. So when we're making fermented foods, we're constantly managing our microbial gardens that we don't want weeds in there. And so I think that's a particular challenge with fermented foods. Like much of microbiology, from medical to environmental, we still rely on 19th century methods. Culturing the bacteria, as you would imagine like a microbiologist to do on a petri dish in the lab. That's still the most common way, but it's problematic. And so what we've turned to is to use more culture-independent methods where we don't grow those bacteria on a petri dish, but instead look at their nucleic acids, their genetic material, to inform us of who they are and what they're doing. And there's a lot of power in that because we can look at whole communities of thousands of different microbes with hundreds or thousands of different species all at once. And so it is a very powerful technique. We were able to use the DNA sequencing techniques to reveal the bacteria that cause slit defects. So slits may be nice or endearing to us if we look at a cheddar cheese, but when you're making a lot of cheese and the purpose of that cheese is to slice it or grate it in the large-scale production that this is, you can't have that. They'll have to throw away a lot of cheese when there's a slit. So we helped a company identify which microbes cause this, as they would call it, a defect.